Hi, everybody. Welcome to AP Environmental Science, or APES as we call it. My name's Mr. Sampson, and I'm really looking forward to teaching you this year. So, listen, this is how I teach my class. We do what's called a flipped classroom. So, your homework is to watch the lessons, and I'll talk to you about some options you have there. But basically, you should probably be watching these screencasts on a pretty much nightly basis and be ready when you step into class. The first day of class will start with a quiz on this information here, and every class will start that way, and you'll just get used to it, and maybe you'll hate me for it, but you'll learn the subject matter, and that's what really matters to me. So let's just get on it. Okay, so our first lesson is going to be about sunlight and seasons. So it turns out the sun is really important in environmental science because the sun is basically the giver of life. Okay, we're a solar powered planet. So basically what you need to know is this: the sun is the primary source of energy for Earth. There's very a few things on Earth that don't involve the sun. So basically, all the weather, all the life on Earth comes from the sun. The sun is a medium-sized star. It basically works by converting hydrogen into helium the same way that a hydrogen bomb works. And it's been doing this for about 4.5 billion years. It's going to do it for about another 5 billion years. And it is the driving energy source for everything that happens on Earth, with a couple exceptions. Now, when light leaves the sun, it leaves in all possible directions, and only a tiny fraction of that energy from the sun actually lands here on Earth. Uh, we're quite a ways away from it, but about a billionth of the sun's energy reaches Earth. But that billionth of the sun's energy, it's everything to us. All right, so basically, here's what happens when the sunlight reaches Earth. Several things can happen to it. I won't be talking about energy as a separate unit later in the year, but for right now, let's just say this: that when it hits the Earth's surface, it can either make the surface warmer, be absorbed and converted to heat, or it can be and basically when that happens, that makes the wind, that makes the waves, that makes the weather and everything. Okay, uh, but about 1% of it gets absorbed by plants and converted to sugars, and that's basically what provides the energy for all life on Earth. And basically, this class is mostly about life on Earth and how to try to maintain it in a sustainable way. Now, but let's talk about energy for a second. So, energy is measured, if you don't know this, in units called joules, which we use a capital J to represent. And power is basically the rate at which energy is transferred to something or transformed, and that's measured in watts. So basically, 1 watt is equal to 1 joule of energy transferred every second. So if the sun transfers 1 joule to Earth in a second, we'd say we have 1 watt of power. But it turns out when the sun's rays come straight down on Earth, say like at the equator, at noon on the equator, that's the maximum amount of power that the sun can transfer energy to the Earth at. And that turns out to be what we call the solar constant. And it's 1,300 watts, or 1,300 joules of energy delivered from the sun to the Earth every second at the equator at noon. Okay, we call it the solar constant, and it's this number right here. So, and by the way, that's per square meter, because different amount of light is the amount of area we prescribe is going to determine how much energy we're talking about. So we express it in terms of per square meter. All right, now here's what today's lesson is really all about. It has to do with the angle of light, has everything to do with how much energy is getting delivered to the surface. So basically, if the sun's rays are coming straight down, like this flashlight illustrates, the energy coming out of here is confined to a small area. So there's a lot of energy density. There's a lot of power per square unit, per square meter. But if I tip that same source at an angle, then that light gets spread out over a larger area. And the same amount of energy is coming out of the flashlight, but that energy is being used to heat a larger area, so it heats each square unit of it less. So basically, there's less density of light energy here, so the surface would be warmed less. There's a greater density of light energy here, so it would be warmed more. And that's the basic idea. And so here's some of my artwork. See what you think of this. Okay, so I have this amazing flashlight. It has 1,300 watts, and if I shine it straight down, I have a 1 square meter circle. When it comes down at 90 degrees to the surface, that's the maximum energy I can get out of this. The maximum power would be 1,300 joules per second per square meter, or 1,300 watts per square meter. Now, take that same light source and tip it at an angle of 30 degrees to the surface. So this angle here is 30 degrees. Well, now this area, instead of being 1 square meter like it was here, is now 2 square meters. That means the same amount of energy, all right, that's 1,300 joules per second, is now being spread out over twice as much area. So now I have 1,300 watts per 2 square meters, which means I only have 650 watts per square meter. So you can see tipping it at an angle means I have less power or less energy being delivered to every square meter. So if you think about the Earth, well, that makes sense. If the sun's rays are at a low angle, it's not going to warm the Earth as much. That's why in the evenings and the mornings, it doesn't feel as hot, but at noon it does. Now, in terms of the Earth overall, we're going to see in this class that a lot of what we talk about is variations in terms of biomes in different parts of the planet. So let's just talk about that for a second. At the equator, that is a place where the sun is more often directly overhead. And so the rays from the sun come in at the same angle parallel on all parts of the Earth. But here they get bunched up. They land in a small area, so they heat this surface more. So here we have 1,300 watts per square meter. But as we move closer to the poles, then what's happening is the angle at which those rays are hitting is getting more spread out. So they're spread out over a larger area, so there's fewer watts per square meter. So, of course, it's going to be colder here than it is here. So the reason it's cold as you get to the poles is because the sun's rays are spread out over a larger area. And when we get to the equator, they're bunched into a smaller area. And the maximum that can be is 1,300 watts per square meter. So this is an interesting little diagram here. So this is basically showing what's called insolation. It just means energy absorbed by the sun. So we see here is, now don't worry about these units here. We'll talk about kilowatt hours later in the year, but the point is look at the shape of this curve. What we see here is 90 degrees. That's the poles. There is some energy absorbed from the sun even there, right? What we find is it increases tremendously as we get to the equator and then drops back down. And here's why this is going to be important in our class is one of the things we'll talk a lot about is biodiversity. And it turns out that the more energy that's being delivered to a given area, the more life that can be supported and the more variable that life can be, the more different species that can exist there. And so the more variation in life that can exist, we find that biodiversity is very much something that changes with latitudes because of these varying amounts of insolation or solar energy that arrives at a given unit of Earth's surface. Now, to make things a little bit more complicated, but important to know, is that the Earth's axis of rotation is not perpendicular to its orbital path around the sun. And as a consequence of that, during certain parts of the year, our axis is tipped up to 23.5 degrees towards the sun. And sometimes 6 months later, it'd be tipped 23.5 degrees away from the sun. So that 23.5 degrees is a rounded number, but that's an important one to know, okay? So Earth's axis is not vertical, as it goes around the sun, it's tipped 23.5 degrees. And so that's going to have a lot of effects on how much sunlight is arriving because it changes the angle of the sunlight as we move through the season. So let's see if we can figure this out. Okay, so by definition, summer is the time period when the axis of the Earth in the hemisphere that you're on is tipped towards the sun. So in summer, you see this 23.5 degree tip is tipped towards the sunlight. And what that does is that puts the sun higher in the sky. So the rays are more closely packed together. They're arriving in a smaller area. So there's a higher amount of watts. We're closer to that 1,300 watts per square meter. But in the wintertime, the rays are going to be more spread out. We'll just stay in the northern hemisphere. So in the northern hemisphere, we say summer, winter, we're referring to the northern hemisphere in this case. In the northern hemisphere, what we find is the rays are now more spread out. They're coming in at a low angle, so we should expect them for it to be colder. Now, that's why we have warm summers and cold winters. It just has to do with primarily the angle of sunlight in the sky, and that varies with latitude. Now, it's worth noting that when it's summer in the northern hemisphere, it's also winter in the southern hemisphere, and vice versa. Now, this diagram shows the Earth making its orbit around the sun, not to scale. Okay, notice that the axis of the Earth always points to the same place. It points to the star Polaris, the North Star. And so it always points in that direction. So that means that at one point in the year, our axis is tipped away from the sun, and then 6 months later, it's tipped towards the sun. And so rather than call it the winter solstice and the summer solstice, that's going to be confusing because we have two hemispheres that are on the opposite schedule. So it's better to call it the December solstice. Now, the term solstice just refers to the shortest or longest days of the year. We'll get to that in a minute. But basically, we should think of it as tipped closest to or farthest from the sun. So the December solstice, we're oriented this way, and the summer solstice, I'm sorry, the June solstice, we're pointed this way. Since we live in the northern hemisphere, the June solstice is when we have our summer because the sun's higher in the sky, and the December solstice is when we have winter because the sun is lower in the sky. And again, the difference is 23.5 degrees. So what that means is uh, that we're 23.5 degrees uh, lower in the sky here than we are here, and 23.5 degrees higher in the sky here than we are here or here. Now let's talk about here and here. So there are, just as we have two important days, the December solstice and the June solstice, which happen on the 21st of the respective months, we also have what's called the equinox, which basically means equal nights. And it basically means there are 2 days out of the year where everyone on Earth gets 12 hours of daylight, 12 hours of darkness, and that is the March equinox and the September equinox, which tend to happen again on the 21st of each month. And that's really, on these days, the pole is not tipped towards or away from the sun. It's at a right angle to it. And on those days, everyone experiences the same number of hours of daylight, 12. Okay, I'm not sure what I have this little box here for, but basically, think of it this way. Here is the path of the sun through the sky from morning to evening on the equinox. In the summertime, it's going to be 23.5 degrees higher than that, no matter where you are on the planet. And in the winter, it's going to be 23.5 degrees lower than that. And so that changes the angle of light, and that changes the amount of insolation. It changes how much energy the Earth is absorbing and how hot it gets, and how much life it can support. Now let's talk about the tropics. I'm sorry, there's a lot of information here. Hopefully some of this you've had before, but if not, you're just going to figure this out. So here you go. 23.5 degrees is the number to know. Here's the equator. It's 0 degrees. Okay. If I go 23.5 degrees north of that, I get what's called the Tropic of Cancer. Go 23.5 degrees south of that, I get the Tropic of Capricorn. I'm sure you've heard the word tropics. Here's what tropics means. Tropics are the areas that are located within 23.5 degrees of the equator. And in these regions, there's going to be 2 days a year where the sun is directly overhead. If you go outside the tropics, there's never a day when the sun is directly overhead. I mean, technically, at the 23.5 degrees, there's 1 day of the year where you get the sun directly overhead. But the point is, once you get beyond there, it's never directly overhead here, and it's never directly overhead here. Then we have within 23.5 degrees of the poles, sort of the opposite situation. We have these very cold areas rather than tropical areas. So we have what's called the Arctic Circle, is located 23.5 degrees from the North Pole, and we have the Antarctic Circle, which is located 23.5 degrees from the South Pole. And in these regions, there are times when you have 24 hours of daylight or 24 hours of darkness. So in this diagram here, since this is tipped towards the sun, this is the northern hemisphere, within the Arctic Circle, we're getting 24 hours of daylight and no hours of darkness. Whereas in the Antarctic Circle, we're getting 24 hours of darkness and 0 hours of daylight. But you can be anywhere in between there. So you can have 1 hour, 2 hours, 3 days. It varies how close you get to the pole. But the point is, there are times when the sun never shines and times when the sun never sets. Those situations can only occur within the Arctic and Antarctic circles. Now take a look at this. So as you move away from the equator towards the poles, you get a greater and greater variation in the amount of time that the sun is out on a given day. So the hours of sunlight. So if we just say length of day in hours, here's what we find. At the equator, it's 12 hours every day. Day in, day out, there's never any variation. If you are at Quito, Ecuador, which is located on the equator, every day is 12 hours long, every night is 12 hours long. But as you start to move away, look what you get. So if I go 35 degrees away from it, we get, oh, look, in the winter, must be in the northern hemisphere, our days are like 9.5 hours long, but in the summer, they're like 14.5 hours long. So there's a bit of variation there. As we get farther away from the equator, we get even greater variation. So 50 degrees, that's basically where I'm used to living. Our days get very short. You have like 8-hour long days in the wintertime, but in the summertime, your days last like 16 hours and 17 hours. And this can be even more extreme. So if we go all the way to the Arctic Circle, what we find is on the day of the winter solstice, the December solstice, the sun doesn't come up. And on the day of the summer solstice, the sun doesn't set. Right? but those are the 2 days, right? Okay. But then if I get within the Arctic, if I go all the way to the pole, look what happens. At the North Pole, it's 24 hours of darkness, 24 hours, and then the equinox comes and you have 12 hours. Everybody gets a 12-hour day, 12-hour darkness, but after that, it's all daylight for the rest of it, and then you get to the September equinox, and then it's all darkness thereafter. So the point is, there's a lot of variation in the amount of hours of daylight and the angle of the sun in the sky. And those two things affect insolation, or how much energy is absorbed from the sun. And so this ties it then back to why do we study this in environmental science? And the reason is this: we're very much interested in biodiversity. And what we find is this graph shows how much energy is arriving at Earth in different regions of the Earth. And we see very clearly is within the tropics, there is a tremendous amount of light energy. So there's a tremendous potential to have life, biotic potential there. But as we move closer to the poles, we get less and less of this. So we find that there's fewer species and just less what we call biomass, less material of biologic origin that exists in these given regions here. And so we find is basically the light tends to be weaker here, and there tends to be longer periods of darkness in the wintertime, where here the sun is usually pretty directly overhead, and the days are never particularly short. So there's never a period of time where plants can't live. Whereas we get farther north, obviously, like even here in Korea, the trees have to drop their leaves in the winter because the sun's just not high enough in the sky, and it's not up for long enough during the day to make it worth the effort of the plants to try to engage in photosynthesis. Thanks for watching. I promise you most of my screencasts will not be this long. But please make sure you know this information, because you're going to have a quiz on this. First thing, when you come into my class, the first thing that's going to happen is we're going to have a quiz. You're going to hate me for it, but you're going to learn, and you're going to get a 5 on the test. So take care.